All right, guys. So here's what we're gonna do. We're gonna talk about how to do these graphs more accurately. And just so you know, like what the end goal is. If we go to the middle of these notes, the notes I just handed out to you guys, if we go to like page 9 where the homework will be, the plan is to be able to do a graph like number 1, that's a polynomial function, with a high level of accuracy, knowing where the highs and lows are going to be. Also, just like how it kind of like twists and turns. Like there's something called concavity. We're going to talk about that today. That's another polynomial, number 2. Uh, even number 3. Number 3 is going to be a little crazy. That might have a cusp. We're going to talk about it. And then number 12, rational function, which you guys have done before, but we're going to be even more accurate with how we graph these. So we're going to be really, really intentional about how we do these graphs. That's our plan for today. But we need some skills, right? But a lot of these skills should come pretty naturally because we've done so much work with derivatives now. So these are more applications of the derivative. So again, we'll start with extreme values. So extreme values. There's a theorem called extreme value theorem. I'm not going to talk about that. I don't want to get too much into theory. But one thing that is important to know is that when you're at endpoints of a graph or critical points, I'll talk about critical points in a moment. That's where the extreme values happen. So, for example, I would consider this to be an extreme value. In fact, I'll call this an absolute max. Likewise over here. It's pretty clear that's the highest point, right? Now it's also the highest point. But how would I use calculus to help me determine those? Let's start with the second graph. How do I use calculus to figure that out? Derivative. And what has to happen to the derivative there? It changes sign. Also, it equals 0. Yeah, actually, I like what Laura says. Actually, what you're saying is a little better. Derivative equals 0, but even better, derivative goes from negative. Sorry, I meant the other way around. That's really what I want to say. The derivative goes from positive to negative. Because notice the tangent lines are positive before you get to that peak, right? It's kind of like a roller coaster. You're going up the roller coaster, you hit the peak, and then you go down. That's truly what we have to look for. We need to look for that sign change in derivatives. We're going to talk about that today and using sign charts. Here, what's happening in the fourth graph? What do we call that? You guys remember? Cusp, good. So the derivative does not exist. But more specifically, the left-hand derivative is positive infinity. The right-hand derivative is negative infinity. So we're going to explore that. Here, the derivative definitely equals 0, right? But does the derivative change sign at all? No, right? There's zero sign change, right? There's 0 sign change because it just keeps rising, right? So here, f prime is positive. Isn't f prime still positive here also? Yeah. So what am I doing here? I'm doing heavy analysis. I'm analyzing these graphs using the skills that you guys have gained over the last 2 or 3 months, right? No sign change for the derivative. So we're kind of just resting this a little bit. What's happening here, guys?
Vertical.
Yep. Derivative also does not exist. We call it a vertical tangent, right? And here, switch colors for a bit of contrast. LHD equals RHD, which equals positive infinity. Get out of the way. So each of these times we call these critical points. So a critical point is when f prime equals 0 or f prime does not exist. We call those critical points. Sometimes we label them as CP, so critical points, because they are critical. They matter. We care about them. And that's where we're going to see high points or low points or cusp or vertical tangents. Or the first graph is actually a horizontal tangent, believe it or not. It actually is a horizontal tangent, even though it doesn't graze the graph necessarily, but it like rests for a moment. It's kind of like you're going up a roller coaster, then you stop momentarily, and you keep rising. So there's no sign change in the derivative, obviously, at that point. Another other things we're going to talk about too today. We're going to talk about local and absolute extrema. So I think we know if something's absolute, it's like final, right? Like that's it. Absolute is what's going to happen. Local means nearby. Good example could be, let's talk about home prices. Are you guys familiar with like how much homes go for around this area?
Yes.
Okay. So let's look at Redwood City. A little cheaper, but not super cheap. Still have that money, right? So the zip code for Redwood City is 94062. So if you're like, like the Whole Foods is, like there's like Mount Carmel, there's like Edgewood, if you're like where the Stacks restaurant is on your way to San Carlos, all the homes close to El Camino. Well, Woodside is also 94062. Same zip code. Woodside, how much was those homes going for? Like probably 40, 50 mil, right? There's some crazy, crazy expensive homes up there. But where us little, minions live, probably $2 million, right? Or $3 million by El Camino. So you could say, if you're off Edgewood Road, like locally, what's the highest home? Maybe 4 or 5 million. Like there might be one house that might be kind of nice and has a little more square footage. Was that absolute the highest home in that zip code? No. The absolute highest would be up in the hills in Woodside, right? Where, some like, mega billionaire in Silicon Valley. I can't remember who lives up there. Oh, Larry Ellison actually does live up there. He's very rich. So anyhow, he made a lot of money. So absolute means like among everything, the highest. But local means like within the neighborhood, within like the vicinity of the graph, we call it local. So we'll have that discussion in a little bit, to be more precise with that. Actually, speaking of devil, let's do it now. Here we go. This is a great schematic. So first off, this is a closed interval. That's very important. So when you have a closed interval, you must consider endpoints. So endpoints could be absolute, max, or min. That could happen. So where is your lowest possible point here? At what x coordinate? Totally, right? Just look at it. It's the lowest point. So it happens to be at the left endpoint, right? What's the highest possible point here? C4. So it's just the highest peak, right? So cool. Now, let's look at all the other places. So my critical points. Why do you think I'm using the letter C here? C is short for critical point. So critical point 1, critical point 2, critical point 3, critical point 4, critical point 5. There are 5 critical points in between A and B. What's happening at the first critical point? What's happened to the derivative before and after? Does it change sign? If C1 does not change sign, right? There's no sign change. So what's happening? Rises, plans out, rises. So the derivative's definitely 0 here, but is it a peak? No. Is it a low point? No. So it happens to be at the left endpoint, right? What's happening? Rises, plans out, rises. So the derivative's definitely 0 here, but is it a peak? No. Is it a low point? No. Is it a peak? No. Is it a low point? No. Is it a peak? No. Is it a low point? No. How can I tell analytically? The derivative doesn't change sign. Now here, we call local max. What's happening here? If the drift's positive, then whenever that happens, you automatically get the label as a local extrema. Local max or local min. More specific is local max, so it goes from positive to negative. So it's going up, then down. Is that the highest possible point?
No.
Yeah. So this is you have a $5 million house eventually. You're not a billion. You're like a multi-million, right? Funny, that's an analogy I had. Okay, local min. Okay. So you're hitting a low point, right? But is that the lowest possible point? No, that's the lowest point, right? You haven't hit rock bottom. You're just down for a little bit, right? But what happens from an analytical standpoint? If it is negative, then positive, correct. Now here, that happens to be a corner, I guess. Fine. It doesn't exist. But still, do we see a sign change here? Absolutely. No pun intended. Get that? Did I do that? Yeah, see if he did for me. Good, thanks. Don't add to it. These absolutely is a double meaning. Okay. This comes organically, just so you know. Oh, that wasn't done on purpose. Then here, same thing like the first one, like C5. Sorry, like C1.
I don't get that. So.
It's negative, negative, so no sign change. Now, the endpoints are kind of funny. I do call that a local min for the right endpoint because the derivatives are negative before I get there. So we're on our way down before I get to B. So we keep decreasing. So that's the other thing we're going to talk about too, increasing and decreasing. We did have this discussion in our first unit back in August and September, increasing, decreasing. So essentially what's happening when F prime is positive, we're increasing. It's like you're going up the roller coaster. When F prime is negative, you're decreasing. You're going down the roller coaster. When you see that transition, that's when you have local extrema. But then how do you get that absolute label? Because you just look at the whole picture. Oh, that's the highest possible point or lowest possible point. Then you get a special designation. You're beyond local. Now you're absolute. But this is still technically, just hold on a minute. This is still technically a local extrema, just so you know. I still call this local. I still call this local. It just gets an added designation, just so you know. Very good.
Why do we care about that last? Why is that?
It's just more formality than anything else. It doesn't now what we're going to be graphing for homework. I'm not going to give you a restricted domain. I'm going to ask you to graph over all real numbers.
So it's not taking
The derivative, yeah. So the derivative there is not going to be 0 or anything special. It just happens to be the right endpoint. That's all.
Okay.
Yeah. But from an analytical standpoint, you just look at like the interval, like, oh, okay, that's my right endpoint. So it could be one of these things. Okay, so this is good. This is clearly what I want to talk about. The first derivative test. So this is going to involve a sign chart. So I told you when you're doing sign charts like crazy, that's exactly what's happening here. This is a sign chart for F prime. That's what you're going to do. So if F prime changed from positive to negative, so it looks like this. So F has what we call a local max. We call it local max. It goes from positive to negative. But what if I do the other way? A local minimum, correct. You don't have to memorize so much. It's more just understanding, like visualizing it, right? Call it local min. And if F prime does not change sign, so it kind of looks like this. So like a snake or serpentine kind of a situation here. Then F has neither local max nor min. But F prime equals 0. Just so you know. Does that make sense? Questions about this one? So as you can imagine, we're going to take the derivative, we're going to factor it, set equals 0, make a sign chart, and see what intervals the derivative is positive or negative. That's what we're going to help us graph these. And you guys are going to do beautiful graphs. All right. Endpoints. So think of what's happening. What if your graph looks like this? You have a left endpoint. So after A pass A, where are all the slopes here? Or the slopes immediately after you pass A? Positive, great. So if F prime is positive after you pass A, then F has a, I know it sounds a little counterintuitive, it's a local min because everything's right, everything's higher than it, right? After you pass left endpoint, everything just keeps rising. I mean, of course, it could come back down again, right? I mean, not a problem, but everything's rising. But well, I've had this here. It's kind of jagged, but all my derivatives are now negative. So F has a local max. Okay, good. Oh, they can be. We don't know yet because we haven't seen the whole picture. At the very least, you just give that label. So just use common sense, right? Now let's look at right endpoints. What if we're over here? That's B. So right before I get there, my derivatives are positive. That's the local max because we're rising up to it. We're going to the right endpoint. We're rising up to it. So it's a local max. Whereas here, you have that. So right before I get there, derivatives are negative. It's diving down to it. So it's the local min. Again, you don't have to really memorize this. It's just more understanding it. Use common sense. Hopefully that makes sense for that one. Okay. So what will we use to determine whether f prime is positive nor negative? Sign chart. So this is how we're using the derivative to help us. So now we actually get to do some really cool. This is cool stuff. Curve sketching. So questions so far? No? Okay. So yeah, now you're going to actually do some analysis. So we're going to use the first derivative test to find the local extrema. We're also going to graph this too. And now this is an open interval, mind you. So no endpoints. Because what's the domain for all polynomial functions? Yeah, all real numbers, right? Unless I told you the restricted domain, but I'm not telling you that. There is some AP language. Now, this is where I'm going to be a little bit nice with you guys. I'm not going to require you guys to use any formal AP language. I'll let Ms. York deal with that. She'll deal with that with you guys, and she'll crack the whip on you if you guys do that stuff. Because we're not an AP class, but I'm treating this like an AP class. I want you guys to at least have the rigor, right? That's why I say, oh, it's like AP, blah, blah, blah. But in terms of AP language, we see down below, you will need to do that next year. Right now, we're not going to worry about that. So all I care about is the analysis and make sure you guys are doing really accurate graphs. That's what I care about. So let's do this. So first off, we probably want to just factor in general, but what can you factor out in general? What can you take out? What's left behind? Okay. And then can you factor out further, guys? How do I factor out further? Need a little trial and error if you want, or fancy factoring rules. Uh, what the heck's going on here? So minus 4. Wait, does that factor? Oh, it doesn't factor. Okay, never mind. Well, that's a bummer. Never mind. Okay, doesn't factor. Fine, whatever. Okay, whatever. Um, well, where are my x-intercepts then? 0. And how do I find the other ones?
Quadrant.
Yeah, quad form, right? I promise to give something that's nice. Well, that's b squared minus 4ac. Yeah, that's a little nasty. I don't like it either. That's 8, negative 96, plus 96, 105. Okay, don't worry about that so much. That'll be forgiving. But it's like 10 point something, right? But there's not plus or minus. So anyway, we could eyeball it. I think we're okay there. So you have this. I promise you, whatever I give you on a test will factor nicely. What's your y-intercept? 0, right? Mhm. What's your end behavior? Yeah, this is where I do care about you guys running limits. Yeah, if you go to the left, it's going to be down. And if you go to the right, it's going to be up. You guys okay with that? I'm pretty sure you guys talked about Mr. Van's class. Good. All right. Okay, we haven't done any calculus yet, right? Now let's do some calculus. F prime of x. What's that going to be? Hmm? Hmm? Okay. Now that I promise you is factorable. We're going to set it equal to 0 because this will help us find our critical points. What can I factor out? X squared minus x minus 2. Okay. So far, so good? Yeah? Okay. What am I going to do next? Is that sorry? For that. Sign chart. We do want those y values for sure. Okay. So if you think about it, is f prime positive or negative when x is bigger than 2? Yeah, and because all these are odd exponents, like these are odd degrees for each factor, you have an alternation. Okay. So far we're okay? Okay. I think now I can graph this. I feel confident in graphing this. So let's do the graph. Um, I think here. Okay, I think it's fine.
The sign of the function is
Nope. Derivative.
Did you also want to create a sign chart for
No,
normal?
it's not that. It's not necessary because you have I mean, we have our x-intercepts, we'll be fine. So I think we're okay. Okay, you definitely have an x-intercept at 0, and a y-intercept same place. Now I am going to eyeball the x-intercepts. Root 105 is roughly 10 point something, right? You have to redo it. That's like 13 point something, right? What's 13 point something divided by 4 roughly?
Lower than 3.
Yeah, so somewhere around 3. Okay. Okay, you're doing 3 minus 10 point something. What's 3 minus 10 point something? Negative 7 point something. What's negative 7 point something divided by 4? Yeah, like a little bit to the right, negative 2. Not less than negative 2. Now, if I plug 2 back into the original function, and then 1 back into the original function, I might be off a little bit, but if I plug in 2 into the original function, what would I get? If I plug in 2, I should get 8 minus 6 minus 12. Negative 20? Yeah. Ooh, that's really low. Okay. By the way, that's gonna be a local min because those are my critical points. That's where my high and low points are gonna be. Because we said derivative equals 0 there. That's why. And at negative 1, that's gonna be a local max. I think you guys are right. I'll just double check. Um, yeah, but you said 7? Yeah, correct. Yeah, good. Okay. So it's gonna be way down here. Sorry. So negative 1 comma 7 is like way up here and way down here. So obviously I can't do it too accurately. So you get something kind of like that. Um, Not my best looking graph because I didn't give myself enough space, but definitely you expect something to take on that shape. So now you can find the high and low points, right? Without a calculator. You have the skills to do it. Now, will these be absolute extrema? No. And that's just because of the nature of the equation, right? I have a polynomial and behavior just acts that way. So yeah. So the answer is no. Okay. Questions on how to do that? So that's part of the homework. You have a homework problem kind of like that, right? Um, okay, we still got a little more time. Let's talk about concavity. Concavity gives you a little bit more confidence. Because here's the thing. This is y equals x cubed, right? Notice how it kind of bends and turns a little bit, but like how come it doesn't do this? Like, why does it have to have this flattening out thing? And there's something called concavity. Concavity talks about how it twists and turns. So here we go. Let's talk about this one. So exert for the following graph, measuring all the tangents from negative infinity to 0. What can you say about the curve here? Well, right now, my tangent line is very steep, right? What happens to my tangent lines as I get closer and closer to 0 from the left side? Right. What's happening? They're decreasing. So f prime is decreasing. It will be a second. Yeah, we'll talk about that in a moment. But f prime is decreasing. Kind of like acceleration, right? Like you're still going forward, but you're slowing down. So what we can say about the curve here, it's increasing, but slowly. And what's happening afterwards? Increasing quickly. Here f prime is going to be positive. But f prime's increasing. Well, of course, they're all positive. Sorry, that was dumb. Of course, f prime's positive here. But what's happened to the tangent lines? They're increasing quickly. It's kind of like when we talked about the flattening of the curve during COVID. So if you want the curve to flatten out, you want that left side, right? You want people will be getting sick, but eventually the rate drops, the infection rate drops. Where people get sick, so quickly, the infection rate's high, right? So we say we're concave down. So this is considered concave down. That's considered concave up. You're concave down when your derivative is decreasing. You're concave up when f prime or y prime is increasing in value. You can also think of this as a frown and as a smile. Not the best way, but like, for example, is that person happy or sad? They're sad. Yeah. Because what's happening? It's positive. The person was in a good mood. Then they got flat and they got really sad. They're down. They're decreasing. They're depressed, right? Okay. How about this dude? It's happy. Was feeling a little down, got to a better mood, and now it's really good. So y equals x squared, by the way, is concave up. Y equals negative x squared is concave down. Another way to think about it too are the tangent lines. I'm going to write this as a text box. If the tangent lines are below the curve, concave down. If above the curve, concave up. Oh, sorry. Yikes. I can't wait to do that. Sorry. That was terrible. If the curve, my apologies. Yikes. If the curve is below the tangent lines, concave down. If curve is above the tangent lines, concave up. My apologies. That was terrible. Yeah, because take a look at it, right? This curve here, these tangent lines, so that the curve is below the tangent lines, right? So when the curve's below, that's concave down. When the curve's above the tangent lines, it's concave up. So if that helps too. But we're also going to relate this to the second derivative in just a moment, because the second derivative also plays a role here. So remember, we have a test for increasing, decreasing intervals. Very good, yeah. Oh, okay, no worries. Okay, good. So now, so we have a test for increasing and decreasing intervals, right? So, um, so obviously, when f prime of x is greater than 0, we're increasing. When f prime of x is less than 0, we're decreasing. And y double prime is the derivative of y prime. So here's something called the concavity test. You're concave down when y double prime is negative. You're concave up when y double prime is positive. We say twice differentiable because you got to be able to do it twice to do that. So let's talk about the concavity of this graph right here. And before I do that, let's actually go to Desmos really quickly. So y equals x to the 4 power Nice. 4x cubed. Okay. So kind of a funky graph, right? So what's happening here is that obviously we're decreasing, but notice how the tangent lines are going to get less steep as I get closer to zero. Plus, if I drew a tangent line right now over here, if I drew a tangent line, okay, that was a terrible line. A little better. Is a curve above or below that tangent line? And plus, it looks like it's part of a smiley face. So that's going to be concave up. Plus, the derivative values are gaining. They're getting higher. The derivative values are getting higher. But then we flatten out. Then all of a sudden, my tangent lines are still negative, but they're getting more or less negative. Yeah, so now they're dropping. They're losing value. The derivative values are actually going down. Now our concave down. Plus the curve is below the tangent lines. But let's actually do this analytically. So here's how you do it analytically. Let's take our derivative twice. So what's my first derivative going to be? Right, and we're not going to find the local extrema because that's not the intention of the problem. We could if we want. Now let's do the second derivative. What's the second derivative here? Minus 24x. Set equal to 0. We can factor out x minus 2. So we still call these critical points, by the way. I'll still call them critical points. X equals 0 and 2. And what I'm going to do with that, do a sign chart. But this is a sign chart for f double prime. And why do I want to do f double prime? Because I'm looking at how the derivative is changing. If f prime is positive, sorry, if f prime is increasing, then clearly, yeah, if f prime is increasing, then f double prime has to be positive. If f double prime is negative, then f prime is decreasing. So if I plug in anything larger than 2, it's positive, then negative, then positive. And you're going to give these as open intervals, by the way. That's because when f prime is equal to 0, that's something else. You need the concave up nor concave down. So you can give these as open intervals. Your concave up from negative infinity to 0, union 2 to infinity, right? Your concave down from what to what? 0 to 2. And you give them as open intervals, by the way. So questions? Okay, one last thing I want to talk about. Then we're all done. Something called a point of inflection, which ties the concavity. A point of inflection is when the concavity changes sign. That's called a point of inflection. So it's not necessarily, either it can be, not necessarily when f prime equals 0. So what we're going to do, because it'll help us to see like, oh, like why is it like, see how like it does this, and then it does this little turn there. That's how you can actually be accurate with it, because what you're doing is you're looking at concavity. Then notice how it kind of like stays concave down, and of course it's this low point way over here, and then starts rising again. But there's a point somewhere in the middle of this. We could do this in a moment, where the concavity changes. It's not very clear on the original graph, but there's a moment where it's concave down, and then all of a sudden it becomes concave up. there's that transition. That's called a point of inflection. It's not obvious from the original graph. It's actually really hard to tell. But analytically, we could tell, or from the derivative graph, we could tell. So here's what we're going to do. Let's find my first derivative, which is 30x4 minus 15x squared. Let's find my second derivative, which is what? 120x cubed minus 30x. Set equal to 0. And what can I factor out? That's 4x squared minus 1. Can I factor in further? Guys, remember different squares? Okay. So far, so good?
Like X squared or something, the ones you take the second derivative, you get like 1.
Give me a moment. I'll talk about that. That's good.
Oh.
It's like, why are we taking the second derivative? Like, does it represent anything?
The concavity, whether concave or concave down. Correct.
Yeah, I didn't.
Exactly. Right. That's exactly it. And we're going to see an alternation in signs. Positive, negative, positive, negative. And so whenever there's a sign change, your points of inflection, I call them POI for short, are -1/2, 0, and 1/2. So when we look at the graph, and we'll actually graph this in a moment so you can see for yourself, that's when you're going to notice this transition in the concavity.
However, the only points where it actually turns are the
Correct.
x-intercepts of the first derivative.
Correct. So if I type in this one really quick and we'll do the quiz. 6x raised to the 5th power minus 5x raised to the 3rd power plus 3. Yeah. So see how do you know that? Like, see, how would we know that, right? How would we know these twists and turns, right? Well, here's what's happening. At -1/2, it's kind of hard to tell. But there's a moment where, see how it's concave down before I get to -1/2? Then it's concave up. So it's almost like, let me get a highlighter. That might be really good, actually. See, that's concave down until I get to here. Then it's concave up. Then it's back to concave down. Then it's back to concave up again. So you want to be kind of intentional of like how we show those twists and turns. Of course, the high points, low points from the derivative. We know that.
When we're graphing this, oh, you don't want to make a sign chart of both.
Correct.
And second
Correct.
derivative.
Correct. Right. No, you're just graphing the original function, but you're doing sign charts for both to do an accurate graph. Exactly. Right. How it's twisting and turning. So anyway, but we're gonna spend more time with this on Wednesday. So, and then the rest of the page here we could talk about next time. But there are some misconceptions you have to be careful about because it's not just because second derivative is 0 does not mean it's a point of inflection. It actually has to see a sign change in the concavity. So, what do you got?
No way to find it without taking the second derivative.
It's like, it's.
No, you need to go for that.
Yeah, 0 can be 1.
Okay. I'm gonna give you guys a little bit of heads up here. This is actually a pretty hard quiz. But if it doesn't go well, I did a second version and I'll replace it. Give it your best shot. You'll see.
Wait, this is on. Who are you concerned?
You get 8 minutes.
Any logarithms?
No, this is hard.
It's chain
It's
rule,
hard.
right?
It's chain rule. It's chain rule.
6 in a row.
Wait, I see his graph.
What the heck?
Okay.
These are AP style questions. Okay, so yes, I'm not doing AP language, but it's an AP style. I know. It's
Oh, it's just a
it's rigor. So rigor. I'll live with that.
So what's the question?
Yeah, what's the question? What is it asking?
It's just a statement. Yeah.
Hold on. Hold on.
Maybe we don't.
I agree.
No, I know you're gonna do it. You're gonna do it. You're gonna do it. Hold on. My bad.
Oh, it's the derivative of GX. Yes, that is true.
Is it one question? Oh, okay.